And a step forward, the full implicit method, it's the Crank-Nicholson method. Actually, in this case, we are going to apply it for the Black-Scholes equation, but actually the strategy in order to get that method is actually the same, the one we followed in the case of the diffusion equation. Basically, it's an average of both explicit and fully implicit methods. So here on the left, we have the finite difference representation for the time derivative, which is actually the same, because actually it's the same for both the explicit and fully implicit methods. And here on the right-hand side, we have an average. That's why we have 1/2 and 1/2. The finite difference representation corresponding to the fully implicit method. Okay, as you can see here, all the values of the B options are evaluated at time j plus 1. And another finite difference representation corresponding to the explicit method. As you can see here, everything here is evaluated at time j. What we are gaining here is a more accurate representation for finite difference representations. You can see here it depends on several a, b, c functions. In the full implicit method, they all depend on j plus 1 time, and the explicit method it depends on j. You can see here which are these a, b, c functions, the ones that are coming from the Black-Scholes equation. Okay, that's the finite difference representation we have in the Crank-Nicholson method. Now what we can do is that we will bring on the left-hand side everything which depends on j plus 1, and on the right-hand side everything which depends on j. And that's what we have here. That's the finite difference representation, as you can see, and as we did in the fully implicit method, we have defined, in order to look it nicer, we have defined some capital A, B, C functions that are the ones you can see here. It's important to note that these ABC functions, the ones that are arising in this Crank-Nicholson method, they are a bit different than the ones that we have defined in the fully implicit method. It's important to take into account it. So in order not to mix the ABC functions arising in the fully implicit methods and the ones that are arising in the Crank-Nicholson method, they are just some functions that we're defining in order to look nicer the finite difference representation we do have here in the Crank-Nicholson method, so that we can elaborate and manipulate these expressions much easier. So as you can see, these capital A, B, C functions, they depend on the small a, b, c functions that we do have at the in the Black-Scholes equation. And besides that, you also have this new one and new two, which are this one. New one is delta t over square of delta s, and new two is delta t over delta s. So this is the finite difference representation from the Crank-Nicholson method. And you can see here again, these equations only holds for this n index going from 1 to ns minus 1. And then we have to consider the boundary conditions in order to supply for these two Mission equations we do have. And for that, as you can see, this is also an implicit method, in the sense that we cannot extract from here an explicit expression for this v and j plus 1 as a function of the values of the option obtained at the previous time step. We don't have an explicit finite difference representation for that. That's why, in order to elaborate that and implement that method, we need a matrix representation and work with the matrix representation. That's what we did in the fully implicit method. And the next, what we're doing is we're going to present the matrix representation for this Crank-Nicholson method.